Okay, forgotten to record it. What have I done now? Okay, so we are basically just to review that. Okay, we are basically looking at this rectangular coil and consider the field as uniform, horizontal, and then this coil is rotating at constant speed. Right? We are going to look at how the flux linkage changes as it rotates. Initially, it's horizontal, and then how the induced EMF will change. Right? We're just applying what we have learned so far. Right? We want to sketch a graph of flux linkage varies with time, and the induced EMF varies with time. Okay, so if you pardon me, I'm trying to help you see that this is horizontal. The coil is horizontal at time t equals to 0. Right? The flux linkage is 0. Right? No area, 0 area. Then, right, is initially is trying to show you horizontal like that. Right? Then it's rotating. Right? Horizontal like that. Then it's rotating that. What's that? Sorry. Haven't got my direction right. Okay, so initially it's horizontal. It's turning out like that. Turning back. Okay, horizontal time equals 0. No flux linkage. And after that, a quarter of the period. Right? Remember, from horizontal to vertical, a quarter of the period. Flux linkage is maximum. Usually we call it phi naught lah. Right? Phi put a naught there lah, or 0 there lah. And then after that, the x come down here, becomes horizontal again. The flux linkage equals to 0. Right? So if you look at the side view here, from here, then you see it has horizontal. This part is vertical. This part horizontal again. Right? Where this previously this is x, now this is x here. That's your front view. Okay, so you choose an easy one lah. Right? So that's a sine curve. We can write the equation down. And then we have said previously, EMF induced is just the gradient of tangent to the curve. So at this part, it will be maximum. At this part is 0. At this part is maximum, but it's negative. Then we can draw. Okay. And then the phase difference between the two waveform is what? Anyone? Speak a bit louder. What's the phase difference between the two waveform? Yep. Anyone? Right, look at the maximum.
180.
90.
180.
No, 90.
Oh,
180, this one must be 0. This must be 0. Question. Why did I put a why did I start negative here? Anyone? Huh?
Lens law. So screen disappeared.
Sorry, somebody is trying to talk. I'm trying to see what is the thing. Not 180, 90 only. Sorry, still learning all this. Look at the maximum. Maximum here. From this one to here is 90. This is another 90. This is another 90. Right? So this is only 90. Right? Why instead of maximum I put minimum here? Anyone?
Oh, because it's vector.
Again?
Vector.
No.
Alternating current.
Good try. Anyone else?
Alternating current one.
Lens law.
Lens law. Thank you. There. We go back to C. That one. The negative sign there. Right? But exam, you don't bother lah. You want to put positive or negative because it's just Lens law as well. So examiner don't bother lah.
So I want to take photo.
You want to take photo.
No, page 19, page 19.
Ah, which one?
Page 19. The previous one, previous one.
Previous one. You want to take photo. This one.
Yeah.
Okay.
Okay, sir.
Don't get confused with here. Right? Here we didn't differentiate this one. That's why I say 180 degrees. Okay, hope you have got your photo.
Yeah.
Okay. Look at the maximum or look at the zero. That 0 and 0. And from here to here is 90 only. And then 90, and then 90, and then 90. That's how you count. If you count period, this is a quarter, this is half, this is 3/2, this is D. Okay, it doesn't matter. You can start
So
maximum.
why the magnetic flux is 0 at time 0?
Initially 0, at time 0, horizontal, no flux linkage. Why not is the maximum value, DAN. Okay. Right, or as I say, differentiate this one. Since most of you would have studied sign by now, or A2, can differentiate it. For those who are good in maths, to get your answer. And then we know, right, your amplitude or your E naught, right? E naught, this is your E naught. Amplitude depends on phi naught and omega. Easy to understand. You turn the coil faster, the EMF maximum induced will be larger, right? It cut faster, more flux cut, more EMF induced. Okay. So E naught depends on the rotation. Besides depending on the flux linkage, the maximum flux linkage also depend on the how fast it rotates. Right? Remember this amplitude and this amplitude need not be the same. They are on different scale. We know this is maximum only, and this is minimum. Right? You can draw. I've given you this one in your book there. Right? It's this one. It's still 90 degrees. Doesn't matter. Why is the induced EMF maximum when the coil is rotating from the horizontal position? Anyone? Yep. Okay. 2 slides back. Okay. Some of you still want to photograph this one. Sorry, computer cannot draw that nicely. That's the reason I have to go to internet to get a better picture for you. Right? As I say, it doesn't matter whether you start with minimum or maximum here. Doesn't matter. Right? The right one is this way lah. Correct lah. This is the right one. But as I say, examiner don't bother about the negative sign because it is Lenz's law only. Okay, hope you have got it. Yeah. Anyone like to try this one? Why is the induced EMF maximum when the coil is rotating from horizontal position?
Because the force is normal to the direction of the field.
Normally, when we come to rotation, we don't use force anymore. We use what? You got the right idea, except you use the wrong term.
We use magnetic flux change.
Torque, not force anymore. Torque is maximum when it's horizontal. Right? When the coil is horizontal, parallel to the field, right? Parallel to the field, the force is up, one down. So it's maximum torque there. After that, it's zero torque at the maximum there. Right? When the coil is vertical, it's 0. Okay, have you got what you want? Or maximum horizontal, it decreases to 0 when it's vertical. So maximum torque means maximum rotation. No? It rotates faster. Flux change faster. This one we have answered already. The phase difference between the flux linkage and EMF. Okay, got.
The magnet is curved already, ma.
Don't bother about the magnet curve. Don't concentrate on that. Just now I told you, you just imagine it's a uniform field.
Oh, okay.
Okay? The curved magnet, in this case, is trying to make it radial. That means it doesn't depend on the angle, but we are not interested in that. We are interested in the uniform field. Okay? The one radial field. Yeah, right. The curved magnet gives a radial field. But as I said, we are interested in uniform field. Hope we have copy already. Yep. Half pi or 90 degrees. Okay, phase difference is 90 degrees or half pi. Okay, this one just show you how the EMF changes. Right, when it's horizontal, EMF is the largest. When it's vertical, EMF is 0. Right, all this can get from the internet. Okay, application. Damping of pendulum. Right, we can use that in what you call electromagnetic brake. Right, where the disc is rotating, the metal disc is rotating, then we want to stop. Right? There's your electromagnetic brake. This pendulum is just showing you the idea. Application of Lenz's law. Okay, we let this this whole piece of metal there, pendulum, swing. Right, we will find that it stopped very fast. After a few swings, it stopped very fast. So you can explain that as it swing, right, the field there will be changing. So there will be induced EMF in the pendulum. Right, as shown here. So remember, where you have induced EMF, your mechanical energy converted to electrical energy. So now the mechanical energy becomes smaller. Mechanical energy becomes smaller, amplitude also becomes smaller. Okay with that? So usually we, instead of calling it induced current, we call it eddy current. Right? Because induced current is usually more beneficial. Eddy current is something, it wastes energy. Not beneficial, but it's still induced current. Right? It's still induced current. So it just heat up the pendulum plate, that's all. And energy is dissipated as heat. Okay with that? If we put slot there, right, eddy current can be reduced, then we can increase the swing longer. Right? The swing can last longer. Why? Because the eddy current cannot flow now. Induced current cannot flow now. Right? We use slots there. Right? So we can use this. This one you can read yourself. You won't bother about it. Okay, we will have to end in 10 minutes time. Right? There's your electrical braking. You can read from your textbook there. Where we can, instead of using a permanent magnet, we can use electromagnet. Right? One thing good about this electrical braking is that when you have a train moving very fast, then it is good. Right? If you use electromagnet, then this one will stop very fast. Of course, the problem with this electrical braking is that if this is slow, then you have a problem. Right? Because the braking is not that efficient anymore. Right? That's for your extra reading. Okay, jumping ring. There's your core or coil or solenoid. There's your alternating current. Right? So when you turn the alternating current here, the ring will jump up. So if you cool this ring in liquid nitrogen, then you see the jump higher. Right? Why? Because at low temperature, electrical resistance is smaller. Okay, this is also a application of Lenz's law. Let me see whether I can get it for you. This one I've sent to you all to see. Demonstration Faraday's law of electromagnetic induction. Coil of the wire. Ferromagnetic core extending out coil. Coil is connected via a switch to 240 line. There are several aluminum rings. Okay, you can use aluminum ring lighter. First, simple demonstration of Faraday. A light bulb wired to wire. Right, there's a coil, there's a light bulb. Then the current, just show you there's an induced current there. We know that a coil carrying a current gives rise to a magnetic field. Faraday's law says that where this change of magnetic flux passes through the conductor surface, an EMF causes current to flow. So the bulb lights up. In this demonstration, it might not be immediately obvious that magnetic flux is changing. But remember, our coil is connected to AC supply. Current flowing through varying sinusoidal frequency curves. So the magnetic field is also varying sinusoidal at the same frequency. Now, for a more dramatic demonstration, Faraday's law of the effect of lensing. When the current is switched on, magnetic field is produced, produces a current flow in the aluminum ring. Like all currents, this induced current produces magnetic field. Now, Lenz's law states the direction of any magnetic induction effect such as to oppose the change produced. So the direction
Very funny.
must be in opposition to that of the coil. Ring experiences a repulsive force and is launched into the air. We can easily show that the force launching the ring into the air current flowing in the aluminum ring. This time there is a gap in the ring. This is a complete circuit, so no current flow. Right, no current flow in this case. That's why there's no induced current. There's a gap there. It must be a closed circuit. Now, what would you expect to happen? We repeat the experiment with the ring. This time, pull the ring first. You should recall that when we pull the conductor, resistance decreases. This means that the induced current flows in the ring much larger. So the repulsive force. Okay, less resistance, more current flow. The repulsive force is greater, that's why it jumps higher. We've seen what happens when the ring is placed to the right hand.
So I thought if you got gap, then will become eddy current.
If there's a gap, the current cannot flow. So there's no repulsive force.
But then got eddy current, right?
Yeah, we call it induced current. Okay.
Current induced ring Faraday's law uses magnetic field of conditions to coil. Difference to previous demonstration, ring starts very close to the coil, so the repulsive force experienced by the ring when the current is on is very large enough to launch it into the air.
Okay, two forces acting now, the weight pulling it down, repulsive force pushing it up. So if they are equal, then it will stay in the air.
So what if we replace the ring with a thicker one, greater mass? Despite being significantly heavy, thicker rings used to levitate roughly the same height as thinner rings. The reason, once again, relates to resistance.
Right? Thicker ring,
Greater cross-sectional area,
more resistant, less current.
So the current is reduced current in thinner rings. So the increased weight is balanced by a larger electromagnetic force and larger current. The explanation of the jump from levitating ring presented is an illustration to remind that Faraday's momentum. It should also remind you of a couple of key facts about resistance, about magnetic fields, current carrying coil. Actually, the explanation is somewhat simplified. If you're happy with the concept displayed here, you might want to think a bit more about the following. Think carefully about the nature of magnetic field used by an alternating current. Think very carefully about length. The levitating ring demonstration suggests that magnetic field is always repulsive. Is this actually what you expect? And not how to explain levitation. And if you want something else to think about, watch this final demonstration. See if you can explain the behavior of thin aluminum foil ring.
Right? Thin aluminum foil ring. Okay, so we take 5 minutes break. Take 5 minutes break. Okay, take your 5 minutes break. Five minutes break, 5 minutes break. We will end now. Start a new Zoom.